This podcast covers logic gates, otherwise known as how to do something useful with all those ones and zeros we've been dealing with. So processing ones and zeros is not surprisingly done using electronics, and that's really what logic gates are in the real world. Now, to help us understand what goes on inside logic gates, we have two other tools that we're going to use, models of what happens. One model is called a truth table, and the other model is called Boolean expressions, otherwise known as algebra, although it's a very specific kind of algebra, as you'll see later on. So let's start with the simplest possible gate we could find. It's an inverter, and all it does is take zeros and turns them into ones, and it takes ones and turns them into zeros. So we read this diagram by saying A is an input, it goes through the inverter gate, and then turns into X. We represent this in a truth table, showing that if A is 0, X is 1, and if A is 1, X is 0. Hence the idea, the inverter. Or A is not 0, X is 0. A is not 1, X is 1. We also express that in a very special kind of algebra called Boolean algebra. The difference between Boolean algebra and the algebra you're accustomed to is Boolean algebra only works with ones and zeros. And it has a special operator, the not operator, which you read by saying x equals a naught. Or you can sometimes read this version of the notation as x equals a bar. Your book uses this notation, x equals a naught, read exactly the same way. And occasionally you'll see computers representing it in a third way. X equals not A, or sometimes referred to as x equals damn it A. Our next gate is the AND gate. It takes two inputs, not just one, and you can see from the truth table that X is 1 only if A and B are 1. You can think of this as a true-false relationship. Both A and B have to be true for X to be true. If only one of A or B is true, then X is not true. And we write this in algebra using sort of a multiplication type of operation. And that makes sense if you think about it. Regular algebra would tell us if we multiply A times B and either one of them is 0, we get a 0. If A and B are both 1 and we multiply them together, we get a 1. So that same algebra works here in the Boolean form of algebra, where everything is either a 1 or a 0. The next gate, if you could think about the opposite of an AND, is sort of an OR. This gate gives you a 1 if either A or B is a 1. So you can see that there are three different combinations of A and B that give you a 1 for X here. And we write this with a plus sign in Boolean algebra. Now this is a little bit weird. Okay, 0 plus 0 equals 0, 0 plus 1 equals 1, 1 plus 0 equals 1. Ooh, but 1 plus 1 in Boolean algebra also equals 1. Maybe easier to think again about in true and false. True or true is true. True or not true also is true. Not true and not true are not true. Now, gates by themselves don't do much interesting, but if we combine them together, we can do much more interesting things. So we're going to talk about combinational circuits, combining logic gates together to make something. Now, I've described this in algebra. You would read this as A and the quantity B or C. Let's put that together with gates. Right? So at the bottom we have an OR gate, and hence coming out of the OR gate is B or C. We take that and put it into an AND gate with A, and that gives us A and the quantity B or C. Now let's see if we can build a truth table for this circuit and see what happens when A, B, and C are different values. Well, you can probably guess that there are 2 to the third different possible conditions here for A, B, and C. And I've listed them here in this truth table in sort of a counting order. That turns out to be a really handy way to do it. So we see 0, 0, 0, 0, 0, 1, 0, 1, 0, and you'll notice that same counting pattern works. C just flips back and forth between 0 and 1, B flips back and forth in groups of 2, and A flips back and forth in groups of 4. Now let's apply B or C and fill in the next column of the truth table. I just look at those 2 columns and I take the OR operation. Remembering that 0 or 0 is 0, but 0 or 1 is 1, and 1 or 1 is 1, I can see that the value in the B plus C columns match the OR operation. They're essentially just duplicated because if you look at the truth table, the first 4 rows are the same as the second 4 rows, as long as all you're looking at is B and C. Now let's look at the A column and the column we just created, B or C. We're going to apply the AND operation to those 2 columns. Remember that the only time we'll get a 1 from the AND operation is when both columns are 1. So we see that the last 3 rows have a 1 in them and the other 5 rows have a 0. So our truth table for the circuit of a whole is shown here. Now we've talked about NOT gates, AND gates, and OR gates. And an amazing property of those 3 gates is that you can build any computer system in the world you want out of using nothing but those 3 gates. The one you're typing on, for instance. However, there's some other gates that give us some more power and let us do things a little bit more quickly and design more elegant circuits. And we'll just talk about a couple of those next. The first and probably most useful for extending the AND and OR concept is called the XOR gate. No, it's not called a XOR, it's called an XOR. It has a symbol that looks very much like the OR gate but has an extra line next to it. And its symbol in algebra is that weird plus sign surrounded by a circle. You can find those on Word if you do an insert symbol and select the symbol font. And you can see the interesting thing here is that it's really an exclusive OR, that's what the X stands for, in that it only sets X to a 1 if either A or B are 1, but not both. So that's the difference from the OR gate. Now here's an interesting gate called the NAND gate. You could create one of those by just taking an AND gate and sticking a NOT gate at the end of it, and it would cause anything to be a 1 except where you have 2 1s in the inputs. Now why would you want such a thing like this? Well, we'll see a little bit later on that this is a really easy one to create in transistor electronics, and so in fact most computers are built using NAND gates rather than using ORs, ANDs, and NOTs. And if there's a NAND gate, you can probably guess there's a NOR gate. And the NOR gate is exactly like the OR gate, but every value in X is flipped to the opposite. Now I said that ORs, ANDs, and NOTs can make any computer in the known universe. Just NAND gates can do the same thing. You can build an AND, an OR, and a NOT out of NAND gates. And you can build an AND, an OR, and a NOT out of just NOR gates. So NAND and NOR are what we call functionally complete. Using just versions of those gates, you can create any circuit you want. So here's another example of a combinational circuit. In this one, we're actually using the same input twice. You'll notice we've just sort of attached an extra wire, if you will, from A so that it goes into both AND gates. And we can see that we're taking A and B, and we're ORing that together with A and C. Now, using the technique before, try to create a truth table for this. When you've got your stab at it, continue this video and you'll see the answer. Okay, we start with our truth table. Again, in counting order, we have 8 possible inputs. And the first column we're going to create is the A and B column. That should be easy because it's just an AND gate. So all we have to do is look for where A and B are both 1. And that's where we'll see 1s in the AB column. And there they are. Now let's do the same thing for the AC column. We look for just the places where A and C are both 1. And there they are. Our last step is then to take those 2 columns we just created, the A and B column and the A and C column, and OR those together. And with an OR gate, we're looking for a 1 in either column or the other. And there's our result. So our overall truth table for the circuit looks like this. Now those of you who have been paying very close attention will notice something very interesting. This is exactly the same truth table that we saw in our previous example. So AB or AC is the same as A and B or C. Boy, that looks a lot like algebra up there on the top. And as we'll see later on, it really is, although it's a special kind of algebra, Boolean algebra. But perhaps the more interesting outcome is that there are 2 real-world circuits that implement exactly that same function. These are known as equivalent circuits. So as in computer systems design, as in any kind of design, there are multiple paths to nirvana.